Okay, so we said we're now going to start with current, electricity. Now we're not going to escape from electric fields and static electricity just like that, because we start in current electricity. The first question I want to put to you, consider your house. Okay? Where's the power supply that provides your house with electricity? Outside the house, was there a power station there? Where's the power supply that brings electricity to your house? Probably Coburg is about the closest, so that's where that electricity is coming from. Now, if we have a look at a typical circuit, instead of a battery, we'll draw it like a cell, but that's Coburg, so we'll actually do it like that, K. Okay, so that's your source of electricity. And then you've got two cables that come out of Coburg. The one comes out and goes to your house and provides light or electricity for a light, and then back to Coburg. That's a very, very simplified way of looking at it. Now, you also have a switch in your bedroom that is open at the moment, so the light's not burning. How far is your bedroom, this area here? Okay, we can maybe put a little box around it to show that this is your bedroom. There we are. How far is your bedroom from Coburg? Say 20, I think. Maybe even 10 kilometers. Okay, let's say 20 kilometers. Right, how fast does electricity flow through a wire? How fast? Speed of light? 100 kilometers per hour? Faster? 1,000 kilometers per hour? Electricity actually travels at 4 millimeters per second. So how far is a millimeter? How far is 4 millimeters? A little gap between your fingers there. Okay. Travels that in a second. How long would it take to get from Coburg to your bedroom? Good few days, good few years probably. How long do you have to wait before the light comes on when you switch the switch on? Practically instantaneous. So how does that work? The electrons are already in the wire, yes. So this wire, this copper wire, is full of electrons. Where do the electrons come from? They're in the copper. Copper wire consists of, there's a copper atom. And copper is number what? Have a look, have a look. (29). You're too late. Okay, copper is number 29, which means it's got what? 29 what? Protons, but it's also got 29 electrons. And that's copper wire consists of copper atoms, and each copper atom has got 29 electrons. They're not all free to move, but a good few of them are free to move. So the electrons that are going to go through this light are already in that wire. That wire is packed with electrons. Okay? Still doesn't explain how when I close the switch, electricity gets there almost instantaneously when it's only traveling at 4 millimeters per second. Yes?
If you had a pencil, like your finger's only doing
Oh, so you're saying it would be a little bit like as if you took a hose pipe and you filled that hose pipe with marbles. Okay? So you had marbles in that hose pipe. It was filled to the brim with marbles, like that. Okay, what would happen if you were to put another marble in there? A marble over there would fall out, even though that marble only moved at 4 millimeters per second. And as you keep on putting marbles, marbles will come out on this side, so they're all moving. Not a bad explanation. Hi there. No, do you need to? Oh, hello, 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 hi.
We're looking at the primary school, and so we came here as well.
With pleasure. This is a grade 11 class. We're doing electricity at the moment.
Sorry to interrupt.
No problem. You're welcome to join us. We'll record you. We're busy recording at the moment. Okay. Right. Okay, so that doesn't quite explain it, because electrons are so small that if you add up all the electrons that are present, they wouldn't be touching each other. They'd be miles apart from each other. Repulsion, so they don't even have to touch each other. They just, if one moves, the other gets pushed away. Maybe. Let me give you a better explanation. Okay. Let's magnify this conductor. Let's draw it as if it was a battery. And we will draw the conductor thicker so that we can try and see what's inside that conductor. Okay, now imagine you've got a battery. There's your battery or your cell. Okay. Here's our conductor. I'm going to draw it nice and big. Okay, let's draw that negative terminal nice and big as well. Right. Now, remember yesterday when we spoke about electric fields around various shapes? What are the different things that we drew electric fields around? What is the first one? Around a positive point charge. Around a negative point charge. Between two positive point charges, do negative point charges, and a positive and a negative point charge. Where else did we draw electric fields? In a irregularly shaped hollow object. Where else? Between two parallel plates. Now a cell can be imagined as being two parallel plates. Do you agree that that's parallel to that? But look at it from this way. If we were to cut the cell in half and open it up, you'd have a negative plate there and a positive plate here. And what would you have between those two plates? You'd have a field, wouldn't you? How do those field lines run? From positive to negative, parallel lines, evenly spaced. So let's try and draw them. There, that's how the lines run. Happy? That's one line. Let's try and draw just 3. I'm not going to try and do too many of them. They should be parallel. Obviously, I'm not going to get that perfectly right. Right. And happy? Imagine that they are parallel. Right. Let's just go back to that thing that we dealt with yesterday, where we had two metal plates connected to a battery. Okay, which part of the battery was positive? Right. So therefore this was negative. How did the field lines look? They ran from positive to negative, parallel to each other, evenly spaced, starting and ending at 90 degrees to the surface. On the edges, they were curved. Right, nothing new. That's what we did yesterday and the day before. I said to you, what would happen if you put a positive particle inside that field? It would move with the current. If I put a negative particle, that's a negative particle, which way would it move? Does anything have to push it? No. It automatically, as soon as that field's there, that negative particle will experience a force against the field. The same applies here. This copper wire is filled with what? Negative electrons all over the show. I'm just going to draw a few of them. And even if I had a lamp here, they would even be in that lamp. Now the moment I close the switch, how long does it take this electric field to be set up? That happens at the speed of light. Bang. Okay? So the moment the switch closes, at the speed of light, an electric field is set up in that wire. In this wire, an electric field is set up. And immediately, any charged particle that finds itself in this field will experience a force. So if we've got a proton there, which way will the proton experience a force? With the field. Can protons move? They're held fast in the nucleus. They can't move. So they experience a force, but they can't move. Electrons, can they move? Yes. Which way will that electron move? With the field? Against the field. Electrons are negative, so it will move against the field. Against the field. Every single electron, no matter where they are, starts experiencing a force, and because they can move, they move against the field. They're negative. So we don't have to wait for electricity to get to a particular point. Any negative electron immediately at the speed of light, the switch is closed, at the speed of light, the electric field is set up, and those negative electrons move against the field. And that's why you get electricity instantaneously in your lamp at home. You don't have to wait 5 years for the electricity to arrive from Kubert. Okay, understand that? All happy with that? You've got your notes on that? No. Toss them around. Millimeters, approximately 4 millimeters per second. That's in a copper wire circuit. A lightning is not moving through a copper wire circuit. Okay. Right, thank you. Who was collecting for Jonathan? Let me give that to you. We still haven't got anyone collecting for Giovanna. Okay, I haven't made for Giovanna yet, so she's not getting. She's absent too often. So she doesn't get notes. No, I'll make extra copies and give them to you in one go, rather than giving some for Giovanna, some for Jonathan. Okay? Right, let's just read through the first half of page 5. You can do your tearing and cutting and pasting later. What makes a current flow? Which is what we've been asking ourselves here. As soon as the switch in a circuit is closed, the battery, does it have to be a battery? What else could it be instead of a battery? A generator, a power station, a solar cell, anything that generates electricity, okay? So as soon as the switch in the circuit is closed, we normally work with batteries. The battery instantaneously, okay, at the speed of light, instantaneously sets up an electric field inside the conductor. Now we may not realize it, but electric fields don't only get set up where you've got open space. They can be set up in solids as well. The same as the Earth's gravitational field. Does it extend through the Earth? Yes. If you jump down a mine shaft, are there gravitational force fields down there? Inside the Earth? Yes. So those force fields extend through the solid Earth. Electric fields extend through the copper wire. So as soon as you close the switch, the electric field is set up instantaneously at the speed of light. We read on. There's your sketch, very similar to the one that I've got on the board. Any charged particle, so not just electrons, any charged particle within the field will experience a force. electrons are charged negatively and are free to move. So that's two things that count in the electron's favor. One, it's got a charge, and two, it's free to move. Therefore, they move against the field because they're negative, i.e. from the negative terminal to the positive terminal. So you need to understand that and know that. Okay? You don't necessarily have to be able to regurgitate it, but if I ask you to explain it, you should be able to give me an explanation. Right. Okay, let's move on from there. The next thing that I want to speak about conventional versus electron current. How many different types of electricity do you get? Two types. What are they? What? Oh, what are the two types that you think? It doesn't matter if you don't know the names. Non-moving or non-moving. So current electricity or static electricity, yes. Okay, that would be one way of looking at electricity. You get the moving type, the current electricity, and you get the static electricity. Any other types of electricity? Yes. Okay, what does alternating current look like when it goes through the copper wire? So it zigzags through the copper wire. Serious, what would make those electrons do that, Jonathan? Come on. What? Change positive, negative. So what do the electrons do? Okay, so you're talking about direct current and alternating current. Who's heard of DC and AC? Okay, besides them being a rock band, or having been. But in terms of electricity, you've all heard, what is the stuff that we get out of the plug? AC. What does AC stand for? Alternating current. And where do we get direct current? DC. A battery provides you with DC, which is a better type of current. They both got their benefits. Alternating current does the following. Imagine my finger is an electron. It flows that way and it stops. And it goes back. It does this. So alternating current, all you've got, if this is your copper wire, instead of having electrons moving through the copper wire, going around to the battery, back and through the copper wire, that's what direct current does, moves in one direction. Your alternating current electron does this, so it just vibrates backwards and forwards. It doesn't go anywhere. So your lights at home, what are they, AC or DC? AC. So those electrons that have been flowing through that light bulb for the last 2 months, it's the same electron that's going one way, turn around, going back, going around. Just so why does ESCOM charge you? You've got your own. Those are my electrons. I put them in there. I bought it when I bought that light bulb, and it's that same electron that's just going backwards. Why must I pay electricity costs for it? And electricity is not cheap. I should be charging ESCOM. I don't care what they do. Why should I pay them? What are they doing? What gives them the right to charge me? Where are they earning their money? What makes the electron move? What? The electric field. Where does the electric field come from? From the battery or from the power station or from the source? And that is what ESCOM does. They provide the energy to set up that electric field that lies in one way. What does that electric field do the next moment? Runs the other way. Then it goes that way. So the electrons are saying, one way, oh, hold, let's go back. Electrons don't know what to do. They get going forward the one way, one moment, then the field changes. So they've got to turn around and go the other way. And then the field changes and they go back. ESCOM is providing that field, okay? And the field moves your electrons. That's why you're paying ESCOM. It costs them money to provide that electric field. That's all they're providing in the copper wires in your house, is an electric field. And then the electrons, which are yours, now can move in that field. And when an electron moves, what does it do? It causes friction. What does friction cause? Heat. And what does a lot of heat cause? Light. That's all it is. Friction between electrons and the atoms that they're squeezing through causes heat, gives you light. All that ESCOM gives you is that electric field, nothing else. So how many different types of electricity do you get? We've said you've got static, current, DC current, AC current, so you've got 6 different types of electricity. Actually, they all basically boil down to an electric field and electrons that move in that field. Sometimes the electrons just flow in one direction. Here the electrons will just flow in one direction. If this wasn't a battery, if this was Coburg, a power station, they'd flow, turn around, go back, flow, go back, etc. But it still boils down to it. But now, what is this whole thing about conventional current and electron current? Have you heard about that before? No. If I give you the following circuit in an exam, you've often seen circuits like that, and I say to you, right, come and take the green pen and show me the direction of the current. Easy. Gift marks. 10 marks. Yeah, you're never going to have it this easy again. Put in one arrow to show me the direction of the current. Is she right? Conventional current. Are we talking about conventional current or electron current? Is there a difference? What is conventional current? Okay, let's have a look at this whole thing and where this whole debate came from. How long have we got? 10 minutes. Back in the 1800s, people didn't know what electricity was. We know what is electricity. Moving electrons, okay? People didn't know about electrons. They'd never heard of the electron. So the word electron didn't exist. Okay? There was something moving through the wire, that's all. If you take a piece of copper wire and you connect it to a battery, let's say, yeah, we've got a piece of copper wire connected to a battery, and you look at it. Can you see which way the things are flowing through it? Or if you cut it open, check it with a microscope, and if you touch it, you get a shock. Something flowed into me, but you don't know what it is that's flowing. Are you right? Which way did it flow? Did it flow into you or out of you? How do you know? You don't know. So scientists knew that there was something flowing through the copper wire. And some scientists were saying it must be something which is negative. So if it's negative, it will be flowing that way. You agree? Out of the negative and around and into the positive. If it's a positive thing, it will be flowing that way. Out of the positive and around. Would you all agree with that? But they had no clue what it was. So, what would you guess? And this debate went on for years. Eventually there was a massive convention of prominent scientists from all over the world, came together, discussed it, put forward discussion papers, it was debated, it was argued, and eventually went to the vote. And what was decided? That electricity is actually the flow of positive particles. not negative particles. So scientists said it must be the flow of little positives, and I think it's probably natural to sort of, let's go with the positives. Positive things you can think of easily. Why work negative? Okay, it always complicates the maths and so forth. So imagine that it's little positive particles that are flowing around. They're being pushed out of the positive and flowing with the field into the negative. And for years, that's what people believed electricity was. And all the formulas and all the textbooks that were written assumed that electricity was the flow of positive particles. Only years later did a chap by the name of Chadwick go and cause problems by discovering the electron. He said, hold on guys, there's actually a little thing called an electron, and that is probably what's moving. They realized the proton was fixed, it couldn't move. The electron was free to move. And so Chadwick said, guys, at that convention, we actually stuffed up big time. It's not positives that are moving, it's actually the negatives that are moving. That threw everything into disarray. All electricity formulas were wrong. All rules, like for example, if you want to know which way a motor is going to turn, you use what is known as your left-hand rule. Now that doesn't work, you have to use the other hand. And scientists said, are we going to change everything? And the decision was no, let's leave it. The main thing though is when we're talking about electricity, if some textbooks, right to today, will show the direction of electricity in the form of flowing out of positive, around, and into negative. What type of electricity have they shown me there? Conventional current. Is that actually what's happening? No. Right? Other textbooks would do the following. Here's your circuit. There's the lamp. There's the ammeter. And what is actually flowing is what? Negative electrons out of the negative. So how do you know what we're talking about? Whether we're talking about conventional current or electron current. If you're talking about electron current, you always put a little E minus next to the arrow to indicate what type of current you're talking about. Okay, so if you see something like this, what type of electricity am I talking about? Conventional current. How could it also be written? Opposite direction with an E minus. Means exactly the same thing. What is it that's really happening here? Is it really little positives flowing from left to right? It's actually in negatives flowing from right to left. But that is quite acceptable. This is known as conventional current, not convectional. Okay, that's your air currents. We're not talking about that, we're talking about conventional current, whereas the other one is electron current. Yes. What, this? What have I shown moving? So what type of current have I shown there? Electron current. Okay, I've shown the E's moving. And they do move from negative. Okay, the electrons flow out of negative, around and into positive. Out of negative, around and into positive. Okay. So, in reality, what is it that really flows? Electrons. And that's how we should do it. But at school level, we work 90% of the time with conventional current. So if I were to say to you, here's a nice example. There is your battery. Here's your circuit. And I'm showing the current is flowing like that. Come and draw the battery in there, please. If you get it right, you get 10 marks. If you get it wrong, we shoot you. I'm not saying anything. I'm just saying get the answer right, please. Otherwise, that bullet is aimed straight between your ears. $10 for this. It's not. You can get 10 marks or a bullet. Either way, you get something. You don't lose. Do we pull the trigger? Looking at those arrows, what type of current have I spoken about? Conventional. And conventional always flows out of positive into negative. 10 marks for you. Okay, right. Good. Let's just read through those notes. And in your notes, I've said, note that's an N, not a C. Okay? It comes from the fact that that was decided at a scientific convention. Right, that's why it's called conventional current. Right, conventional current is not really what happens. It's theoretical only. It involves the flow of positive particles, imaginary flow of positive particles from the positive terminal around the circuit and into the negative terminal. And it's indicated just with an arrow on its own. Okay? Just like I showed there, just an arrow, nothing else. If we look at electron current, this is what really happens. It involves the flow of electrons. It flows from the negative around the circuit and into the positive. Okay? And it is always indicated with an arrow with an E negative written next to that arrow. And just the bottom line, I don't know if it's come out in the photocopy. Generally in matric or in grade 11, we use conventional current. All your textbooks talk about conventional current. You'll only start talking about electron current when we get to electricity in chemistry, which we will do next year. We'll start involving electricity in chemistry, and then we talk about conventional current. Sorry, then we talk about electron current. Right, any questions? Let's call it a day. Thank you.